Welcome to a new video. This one is about using rectangles to approximate area under a curve or Riemann sums. So let's look at this first example. We want to look at the function f of x equals x squared minus 2x plus 3 on the interval 1 to 9 and evaluate the Riemann sum that satisfies the following characteristics. That interval is divided into 4 subintervals of equal length, and it is evaluated at the left endpoint of each interval. Before we get started, let's draw a sketch to get a feel for what this graph looks like and what we're actually finding. So we'll draw our graph in here. We want to go from 1 to 9, so let's just say 1, 2, 3, 4, 5, 6, 7, 8, 9. And what is this sketch going to be? Well, I see x squared minus 2x plus 3. That's going to be a parabola. So I'm just going to find a couple important points to help me plot a basic shape, not a perfect sketch, just a little sketch, and get a feel for what this is going to look like. So maybe I'll find my vertex, which would be x equals negative b over 2a. So that's negative 2 over 2a, or a, we know what a is. A is 1. So that's 2 over 2, so that's just a 1. So my vertex is at the point 1 something, and I'll just plug 1 back into my original function, plugging it into f of x. If you plug a 1 in, you get a 2 back. So my vertex is 1, 2, so that's the left side here of my interval I'm looking at. And then I want to go up to 9. So let's just plug in a 9 to get a vibe here. If I plug in a 9 squared minus 2 times 9 plus 3, I'll end up with 66. And, looking at, since this is a positive x squared, we know it'll be a U-shaped parabola, not an upside down one. So that gives us a decent idea of what this sketch is going to look like. Let's see, 9 has to go with 66, so I'm just going to count by tens here. So 10, 20, 30, 40, 50, 60, 70. We don't have to draw all of these, but I'll just add my scale to get a feel for what's going on. And if I plot my points, 1 goes with 2, so way down there. 9 with 66, so that's about right there. And I know it's a parabola, so it's going to have this basic shape. Not perfect, but close enough for what we're doing. Okay, so now let's go through what else we need to figure out. It needs to be divided into 4 subintervals of equal length. So let's think about how to do that. I see I need to cover the interval 1 to 9. 1 to 9, that's going to be a distance of 8. And if I need to cover 8 with 4 subintervals, 8 divided by 4 is 2. So each one is going to be a width of 2. So I'm going to come in here and kind of mark every 2 with this hot pink. And we'll see that's 3, 5, 7, and 9. And so that's going to be the base of each rectangle, the width of the base of each rectangle. So I've got those figured out, and now I need to figure out the height of each one. Well, the height is going to correspond to some value along the curve, right? Because we're going to draw our rectangles until they touch the curve. And the key here is we want left endpoints. So what we can think about is, here's my very first rectangle. There's its base is 1 to 3. And if it has a left endpoint, that means I need to look at the value 1 and go up to how high I am at the value of 1 and draw a rectangle. So this first rectangle is going to be that height. My second rectangle, the base is from 3 to 5, and the height is however high the curve is if you plug in a 3. The next one, the base is going to be this right here from 5 to 7. The height is going to be all the way up to whatever you get if you plug in a 5, and we'll figure that out soon. And then my last one, the base will be from 7 to 9. The height will be whatever we get if we plug in a 7. And we have that. So what we're looking at is these 4 rectangles that have an equal width. Let's label each one of them as well. So this first one we'll just call rectangle 1. We'll call this next one rectangle 2, rectangle 3, and rectangle 4. And I'm just doing that so I can refer to them later. And what I want to do now is find the area of each rectangle and then just add all of that together. So I'm going to make a table to make this a little bit easier to keep up with everything I'm doing. So what I can think about is, which rectangle I'm on. We'll start with rectangle 1. We'll do rectangle 2, rectangle 3, and rectangle 4. Um, if I want the area of the rectangle, I need a width of each one. But each one actually has the same width of 2. They're all a width of 2. And then now to find each one's height, what I'm going to do there is I'm going to plug in the left endpoint into my function up here, my function x squared minus 2x plus 3, to figure out the height. I'm not going to estimate based on the picture because I want to do a Riemann sum that actually plugs into my function. So the height of the first one, this first rectangle, rectangle 1, notice its height is based on plugging in the 1. So we will find f of 1. Oh, and we already knew that. We found that earlier. F of 1 was a 2. Remember, if we plugged in 1, we got a 2 back. All right, for my second rectangle, I need to plug in a 3 to see how tall that one is. If I plug in a 3, what is that? 3 squared minus 2x plus 3. And that equals 6. If I clean that up, or not minus 2x, minus 2 times 3 plus 3. That's a 6. F of, now what do I plug in for that third rectangle? My third rectangle, its height corresponds to plugging in a 5. So f of 5, that would be 5 squared minus 2 times 5 plus 3. That's 18. And then finally, f of 7 for this last rectangle. How tall is it? It corresponds to plugging in a 7. That's how tall it was. F of 7 would be 7 squared minus 2 times 7 plus 3. That ends up being 38. And so now I want to add all of these together. So what I can think about is it's going to be width times height plus width times height plus width times height plus width times height. But I'm going to notice that 2, that width is common to all of them. So I'm actually going to undistribute it. I'm going to factor it out and just say 2 times 2 plus 6 plus 18 plus 38. That's just making my calculations a little bit easier. And then when I do that, that's the same as 2. If we add all that together, it's a 64. So that's 128. So 128 square units is our approximation using of the area, finding using a Riemann sum, using 4 subintervals of equal length and a left endpoint. All right, so that's our first example. The numbers worked out kind of nicely because they're all ended up being whole numbers. Let's do another example where the numbers don't work out quite as nicely and make sure we still understand this concept and how to put it all together. Let's now look at this function. It's a little bit different. So what are we looking at here? We're looking at the function square root of 16 plus 4x on the interval -4 to 0, and we want a Riemann sum again. We want to divide into 5 subintervals of equal length and use the right endpoint for each subinterval. So again, we're going to start by drawing a quick sketch to get a feel for what this is going to look like. Before I get started too far, so this square root of 16 plus 4x, that is a kind of in the square root of x family. So remember, square root of x, that basic graph looks about like that. So this graph's going to look similar. It's going to be shifted around a little bit, but it's going to take on that basic shape of a square root of x graph. So let's plot a couple points, kind of think about what this is going to look like. I'm going to plot f of, well, -4. That's one edge of my interval. So if I plug in a -4, I get 16 plus 4 times -4. So that's like the square root of 16 minus 16, or 0. So that's a 0. And then the other end of my interval, f of 0, if I plug in a 0, square root of 16 plus 4 times 0, that's like the square root of 16, so a 4. So that gives me sort of a feel for the edges of the part that I'm plugging in. Let's graph that over here. So let's say 1, 2, 3, 4. So we'll go back to 4 there. And it looks like I need to get up to a positive 4 in my y values too. So we'll sketch that in. And let's plot these points real quick. 0 goes with 4. -4 goes with 0. And I know these aren't going to connect in a straight line because it's going to look like that square root of x function. So I'm just going to sort of curve it. And if I kept going, it would look sort of like that. Does this have to be perfect? No, we just want a basic outline of what our graph looks like to have a visual of what we're actually doing. Okay, so let's keep going. We want to divide this into 5 subintervals of equal length, and we want to evaluate at the right endpoint of each one. So if this is 5 subintervals, well, what is the distance here? What's the distance between -4 and 0? Well, that's a distance of 4. And then I need to divide into 5 subintervals. So each one is going to be 4/5. We can think of that's our width here of each rectangle, the width of the base of each one. Okay, so what does that mean? That's not a nice whole number. In our last example, we had that nice width of 2, kind of let us just deal with integers. Now we do have some fractions, so we sort of need to think about, what is each one of these fractions going to be. I'm going to draw a little table to help me start thinking this through. So I have 5 rectangles. I'm going to have my first one, my second one, third, my fourth, and my fifth rectangle. Each one is going to have the same width of 4/5. They're all the same here. And now to figure out each one's height, I'm going to have to plug in the right endpoint. So I need to think about, what are the right endpoints here. So each one is 4/5 wide. What I can think about, this first one's going to end about right there. It's got to be less than 1 wide. But what is that value right there? Like, what am I going to end up plugging in? Well, I'm going to have to plug in, let's think this through. I'm at -4 and I need to add 4/5 to move to the right. I'm going to change these to fraction. -4 is like 20/5 plus 4/5. So that's like -16/5. So this value right here is -16/5, which means, what is the height of the first one? I'm going to plug in a -16/5. That's my value. And now what am I doing? I'm adding 4/5 each time. So now I can go through that. What's -16 plus 4/5? Well, that'll be -12/5. And then add 4/5 again, it'll be -8/5. Add 4/5 again, I'm at -4/5. Add 4/5 again. Oh, I'm at 0. Oh, perfect, because that's where I wanted to end. So I counted by the value of 4/5. So let's label these all over here. So now I'll be about right there. That value would be the -12/5. Maybe about right here. And that would be the -8/5. And about right here, that would be the -4/5. So I'm going to draw these a little bit larger so we can see each of these bases. This is going to be the base of each of my 5 rectangles right there. Okay. Let's draw them to get a feel for how tall each one is. This one at the right end point, we're going to go up to here and go over. This one will be this tall, like plugging in a -12/5. This one will be this tall, like plugging in a -8/5. And about right there. And then all the way up to 4. So here's my 5 rectangles. Here's my first one, second, third. I don't know why I keep writing a B. Third, fourth, and fifth. So those are my 5 rectangles that I want to find the area of and add them all together. And that gives me an approximation of that area under the curve, that area under the purple part. One thing just to notice right here, I know my answer is going to be an overestimate because do we see we're above the curve? We have part of our rectangles are all hanging out above the curve. So, the area I actually want is this part I'm outlining. That's my goal. Eventually we want to find that area under the curve. we're estimating now, and we've got an overestimate. All right, so what is the height of each of these is going to be? Well, this is where, carry your intermediate computations to 6 decimal places. We're just going to do some calculator help here to help us out. I actually have the table copied here on the next page. I'm going to copy it and paste it in. I've already found all those values. So if we plug in f of negative 16 over 5, we get this value. If we plug in negative 12 over 5, we get this value. So this is corresponding to each of those heights of my 5 rectangles. Again, how did I do that? I just found f of negative 16 over 5. I plugged it into my original function and approximated to 6 decimal places as it asked me to. Okay, so now what do? I need to find the area of each one. The area of each one would be the width times its height, the width times its height, the width times the height, width times the height, and width times height. But because that width is constant all the way through, I can factor it out. So it's like 4/5 times this one plus this one plus this one plus this one plus that 4 on the end. Okay, I'm just not going to rewrite all of those. We see all those decimals in there, which, what is that saying? That's like 4/5 times this sum, a different color. 4/5 times that sum, that 14.999. And when we do that, we end up with 11.9958. And I'm rounding to 4 decimal places because it has asked me to round to 4 decimal places just at the very end. And we want to wait till then. We don't want to round to 4 decimal places in these. We want to go a little further in our intermediate computations and then round to 4 decimal places at the very end. So what that's saying is the area under this curve from -4 to 0 using this Riemann sum set up this way is about 11.9958. I guess we'll say square units. Okay, so that's an idea how we can do Riemann sums, how we can add these together. You definitely need a calculator for these that are going to have lots of decimals in them. But my advice, set up a table to help you keep up with all the pieces, draw a quick sketch to visualize what's going on, and then it's really just a lot of finding areas of rectangles and adding them together. The big new part is figuring out which rectangles, but once you know which rectangles to use, we're just adding up all of their areas. Hope that helps.